Okay, welcome everyone to this continuation of what is tropical geometry. We are already at part 11, and today I will talk about plotting something. A lot of plots, a lot of graphics. Yeah, this is a formal name, but it really means graphical plots, and two ways actually to do plots, and there should be a way to go from one to the other and back maybe, and this is this implicitization. Oh god. What a mouthful. Let's see what this actually is. And it turns out that this is like really difficult in kind of classical geometry and pretty straightforward in tropical geometry. As usual, tropical geometry, or as often, tropical geometry is just so much easier than classical geometry in a certain sense. The first thing I would like to show you is an implicit plot. So this is how I usually like to think about varieties, the zero set of a polynomial. So here I took a rather fancy polynomial, pretty large. So I got that polynomial from the book that I'm using for the course. They have exactly this polynomial here. Where is it? They have exactly this polynomial here. So the book on tropical geometry, really nice, and I kind of feel like it's really impressive. So this polynomial, which is clearly non-trivial, it has already non-trivial as it's pretty large. It has already quite large coefficients, huh? And here's the associated variety. That's how a variety is supposed to look like, I guess. Yeah, and the usual way to plot this is just all points that satisfy this equation, and that's what people call an implicit plot. Yeah, implicit is some graph of an equation where the relationship between the variables is given implicitly. So it's not like something like the usual explicit plot, f of x is y or something like that. Whatever. Explicit example, f of x is x squared or some bullshit like that. So where there is f of x is y is a bit boring. F of x equals x squared, where there's an explicit relation between the two variables. Now in this case the relation is implicit. This is where the name comes from. In our usual way, this is really how we usually plot varieties. Polynomial, whatever, in two variables equals 0. Polynomial in three variables equals 0, right? So implicit and an implicit relation between the variables that we'll see in those plots. And here's the same plot. Well, let me go back. It is indeed the same plot, so I will tell you in a second why the frame looks different, but it's really, really the same thing. And it's the plot of this parametric equation. And parametric is a bit different, or quite different actually, than an implicit plot. So essentially you have something like time goes to x, y, something like that, to a point. Very explicit, right? Something goes to something. This is more like what you have in mind, or what most people have in mind if they think about a graph, right? Something very, very explicit. And I'm not cheating here. These are really the same things. Yeah, so I made those plots in Mathematica. You don't need to. There are plenty of ways to do those plots. And here you can literally see I set up the parametric plot, and it's this rational function in t with two inputs, and I have the implicit plot, and they're really the same. They're really the same. It's very remarkable. So here the standard plot, if you want, and the implicit plot, they are really the same. And if you look at the documentation, in this case, they have some more nice examples. I said again, I'm using Mathematica because I just started using it at one point, and then it's kind of hard to change yourself. You don't have to. Essentially everything, even freely available software, I should promote freely available software. Freely available software can do those plots. But let's, for this video, just stay with Mathematica. So parametric plot is something like that. Huh? So here you can parametrically plot a circle, like using cosines and sines. So you just copy that and just maybe just do it here, paste, I guess, and it should just spit out the picture from before, right? So you can do a circle, you can do an ellipse, then the bigger circle or whatever, and explicit coordinates of the parametric plot. And essentially I'm telling you that works for all varieties. So there are two different ways to think about varieties. As a parametric plot or as an implicit plot. Right? It's kind of nice. And how do you go between the two of them? It's not completely trivial, right? Just look at the example. Let's go back to the slides. Just look at the example here. This is a not quite trivial rational function. Yeah? And this is a not quite trivial polynomial. And it's not so clear how to go from one to the other. And indeed, this is not easy at all in general. There is a method to do it, but it's not straightforward, right? So note the following. I said again. Implicit, we have varieties as zero sets of polynomials. Explicit, we have varieties as kind of images of rational functions. And the way to go between the two of them, which I'm not going to explain in too much details, are essentially Gröbner bases. And the other way around, resultants. What a complicated name. The problem is this is just really, really nasty to compute. Not nice, hard, difficult. Yeah, so kind of makes sense if you look at this thing and you look at that thing. They are not straightforwardly related in any way or form. Another problem is if you do that, usually the Gröbner basis is like something that looks pretty random geometrically speaking, and it's not quite clear what's going on. So this is not great, right? Going from implicit to parametric and back. Yeah, so say it again. Parametric, implicit, two different ways to think about varieties, but going between them is a bit of an. I mean, there's an algorithm, but it's not absolutely fantastic and nice and great. I don't want to talk about it. Yeah, let's be realistic. I don't want to talk about it today. For tropical curves, let's say for curves, it's actually pretty easy. It's surprisingly easy again. It works as follows. So you just have two rational functions, right? So these are first coordinate, second coordinate type thing, rational functions. Let's say in t is our variable, and let's say we work over the complex numbers, then we can just factor them, right? For the complex numbers, there will be some pole or root, depending whether this is a positive or negative exponent, and we can just factor them. And the nice thing about tropical geometry, because we take a log, essentially, is only the exponents matter, and the funny roots that are really difficult, we don't care. So we only keep track of the exponents and write them in a vector like that, and those vectors give us a nice picture, which essentially spans our tropical variety. And that's it. Yeah? So we just need to, this is the way to go from such a plot to such a plot, right? Tropically, it's really easy. Collect the exponents, you put them in a vector. What you see will be, you get a collection of vectors, and the vectors span, well, this guy here, this funny pentagon type thing. Ooh, this was a really bad drawing. I connect the heads of the vectors. Maybe I can try that again. This one was off. The first one was fine. The second one was a bit bad. The third one was a bit bad as well. This one is a bit nicer now. Beautiful. So this type of pentagon is a Newton polytope for our tropical curve. It's pretty simple, and of course there's a higher dimensional version. I was just too lazy to state that. Yeah, and it really works. So I just plotted the tropical curve, and here's our Newton polygon. 1, 2, 3, 4, 5. Wonderful. 1, 2, 3, 4, 5 by just connecting those guys. And it's really, really simple, right? So going in between implicit and explicit plots for tropical curves is actually pretty easy. Yeah, so pretty good. I like that. And so I hope you enjoyed this video. I hope you liked this as well. And I also hope to see you next time.